In this video, I will talk about the avatar adjusted for Serbian language. This project is AI Speak project funded by Science Fund of the Republic of Serbia. This slide shows the core idea of our system. Our goal is to train a deep learning model that takes audio and text as input and predict blend shape coefficients as the output. These coefficients are then directly applied to a 3D avatar to animate speech. In other words, instead of manually animating facial movements, we want the system to automatically learn how facial muscles should move during speech. The challenge here is that speech animation is not just lip opening and closing. It includes subtle jaw, cheek, and lip corner movements that must be synchronized with phonetic and prosodic information from speech. So the full pipeline is text and audio on the input, neural network in the middle, and prediction of blend shape coefficients that will be put in avatar animation. This is the recording from our original dataset, recorded in an anechoic chamber. The environment is acoustically controlled, which is ideal for speech research. Our initial plan was to use these videos to extract facial motion information.
Ponedeljak, utorak, sreda, četvrtak, petak, subota, nedelja.
At this stage, we assumed that high-quality 2D video recordings would be sufficient to derive facial motion parameters for training the model that I talked about in previous slide. Here we see the MediaPipe face mesh. MediaPipe is a real-time computer vision framework developed by Google that automatically detects and tracks facial landmarks. It provides a dense mesh of 468 3D face landmarks covering the entire face: eyes, eyebrows, lips, jawline. So for speech animation, the most important regions are the lips, mouth, corners, and jaw area, since they encode articulation. From these landmarks, it is possible to approximate facial muscle activation and derive blend shape-like coefficients. Here we can see those landmarks on the detected automatically on the video from our database. This figure shows a typical ARKit 52 blend shape system, which is widely used in avatar animation. Each blend shape corresponds to a predefined facial expression or muscle movement, such as jaw open, eye closed, cheek raise, etc. These blend shapes form a compact and standardized representation of facial motion, which makes them ideal as neural network targets. Here we see the original video and the blend shape coefficients extracted using MediaPipe blend shape v2. So visually, the coefficients appear meaningful. When the mouth opens, the jaw-related values increase. When lips close, lip-related coefficients change accordingly. So at this stage, everything suggested that these parameters could serve as good training targets. In parallel, we built a 3D avatar modeled after the speaker's facial features. The avatar is rigged with the same ARKit 52 blend shape standard, meaning there is a direct mapping between extracted coefficients and avatar controls. However, when these extracted blend shape coefficients were applied to the avatar, the animation quality was poor, as you can see on this video.
Ponedeljak, utorak, sreda, četvrtak, petak, subota, nedelja.
So lip movements lacked depth, jaw motion looked unnatural, and articulation was not convincing. This showed that 2D derived facial parameters are actually insufficient for realistic 3D speech animation. The key issue is the difference between 2D observation and 3D facial motion. MediaPipe works primarily from RGB images. Subtle depth movements such as lip protrusion or jaw forward motion cannot be reliably recovered. Speech articulation is inherently three-dimensional. To solve this, we switched to FaceCap. That's an iPhone application that uses the front-facing depth camera to directly capture ARKit blend shape coefficients in 3D. This gives us physically meaningful 3D facial motion data without needing to reconstruct it from 2D videos. So, we recorded a new dataset using this method. Two speakers recorded 180 sentences each. One speaker matches the avatar identity, and the other ensures the model can learn speaker-independent motion patterns. The reason for this is that makes the system compatible with synthetic speech in some future real-time applications. This slide shows the final target scenario. So we have text that we want the avatar to speak. We send it to TTS module to produce synthetic speech. That waveform is actually the input to some deep learning network, which will produce blend shape coefficients that we will use to actually animate this 3D avatar. This pipeline actually enables real-time digital humans driven by synthesized or some recorded speech. So, here we will see animation driven by depth-based blend shape coefficients from our new database.
Ponedeljak, utorak, sreda, četvrtak, petak, subota, nedelja.
Although still not ideal, it is a lot better and more convincing than the previous one. So the motion is much more natural, especially around lips and jaw, and this confirms the importance of that depth information. Now, Serbian has a near one-to-one grapheme to phoneme mapping, and that is something that actually simplifies text processing. Phoneme extraction from text, so for the Serbian language, is straightforward, and that's not the problem. But we need actually VSEMs. VSEMs are the visual counterparts of phonemes, groups of speech sounds that look similar when articulated. While phonemes are defined acoustically, VSEMs are defined visually based on lip shape, jaw movement, and visible tongue position. For English, several predefined VSEM sets exist. These are some of them. Classic and modern systems typically contain between 12 and over 20 VSEM categories, while English itself has 44 phonemes. This means multiple phonemes share the same visual representation. These English VSEM systems are widely used in speech animation, lip reading research, and audiovisual speech synthesis. English has 44 phonemes, while Serbian has, let's say, 30 phonemes. Certain Serbian phonemes, such as lj, nj, dj, ć, and dž, do not have clear visual equivalents in standard English VSEM sets. Their articulation involves specific tongue placements and palatal or affricate features whose visual characteristics are not distinctly represented in English-based systems. Because of this mismatch, directly mapping Serbian phonemes onto English VSEM groups would lead to loss of articulatory information and reduced realism in facial animation. We also explored data-driven clustering approaches to automatically derive VSEM groupings from extracted blend shape coefficients. Methods such as k-means, hierarchical clustering, dbScan, spectral clustering were applied. However, these approaches did not produce visually or articulatory meaningful groups. Therefore, we adopted a linguistically guided approach based on place of articulation and carefully visual analysis of recorded speech. The resulting proposed VSEM mapping for Serbian is the following. So we have first group, bilabial phonemes, p, b, m, labiodental, f, v, dental, t, d, s, z, c, post-alveolar, š, ž, č, dž, ć, dj, velar, k, g, h. Four groups for vowels. First a, second e, I, third o, fourth u, and group other, where we put l, lj, r, nj, j. This VSEM system is considered a working hypothesis and will be evaluated and refined in future studies.